have a quick checkpoint to let you familiar with how to do some cancellation for the symmetrical structure. Okay, so here it says the figure here shows 3 non-conducting rods, 1 circular and 2 straight. This one is circular, these 2 are straight, and each has a uniform charge of magnitude Q along its top half and other along its bottom half. For each rod, what is the direction of the net electric field at point P? Okay, so let's take a look at the leftmost one first. So this one we have Q, negative Q charge equally distributed along the top left part, and then the plus Q charge are equally distributed on this part. Okay, so it asks you the direction of the net E field at point P. Okay, so just as what I mentioned before this lecture or in the previous lecture, so of course this is a continuous charge distribution. So actually we need to separate into many small parts, small segment. Okay, let's say this one is ds, and we can symmetrically find a part called ds prime. Okay, so actually you can see the bottom part and the lower part, which should have a symmetrical axis as the x-axis. Okay, so ds here, ds prime will be the symmetrical segment. Okay, so in that case, this is negative q. This is negative q. So what is the direction of the E field at point P due to this ds? Okay, pointing to should be pointing to this side. So this is DE. Okay, this is negative charge. So the E field at this point should point to this ds. Okay, and then for DQ or ds prime here. Okay, this is positive charge. So the direction at point P will be pointing to the top right. Okay, maybe I write it like this. This is DE. Okay, so this is DE prime. Okay, so the total force, the total E field at point P should be pointing upward. Or upward. Okay, so for the second one is this one. For the whole rod, plus Q here, plus Q here. Okay, so similarly, we try to cut it into many small segments. So this is ds, and the symmetrical part is here, ds prime. Okay, so due to ds, it will generate E field at point P. That will pointing to the bottom right. Pointing to the bottom right. So this is DE. Okay, because this part it has a positive charge. So the E field generated point P due to this part will be pointing to the bottom right. And then similarly for ds prime, this is also positive charge. Okay, so connecting it, so the DE prime will be pointing to the top right. Okay, so when you add these two DE prime together, so the total E field will be pointing to the right side. Okay, so this one, the only different thing is that this part is negative Q rather than positive Q. Okay, so here similarly ds here, and then ds prime here. Okay, so for ds, which will be the same as the question B. Okay, so DE pointing to the bottom right. But for ds prime, this is negative charge. So DE prime will be pointing to the bottom left. DE prime. Okay. So the total E field will be pointing downward. Okay. So far, any questions? 有没有问题？这边就让你们再熟悉一下怎么样去做一些 cancellation 啊。但 cancel 完这一题就没有给数字的话，就没有叫你算这个后面的积分。但是你先知道怎么样去 cancel， 然后后面再写式子的话，就有另外的，比如说 selected problem 啊，那你可以去参考。Okay, so no problem. We move on. So for this one, we have another structure. So this is a charge disk. So here we have a charge disk with uniform charge density. Okay, with uniform charge density. And yeah, so of course the first idea is to separate this disk into many small pieces. So maybe in your mind, your first thought will be considering the Cartesian coordinate 就是用直角坐标系把它切开，就是 it's just like you have a circle and then you try to cut it something like this and then something like this. Okay, this is a straightforward way. So for every pieces will be like dx times dy, something like that, and then okay, within unit area there will be some charge, okay, something like that. But actually this is a circular disk. Using the Cartesian coordinate will usually be not easy to calculate. Just like when you learn the calculus, if you need to integrate the area of a circle, so if you use a Cartesian coordinate, the integration will be something like square root of r squared minus x squared dx from 0 to r, and then 4 times, something like that. This will be the area of a circle. But for this integration, you need to do the u substitution, x equals r times sine of theta, something like that, and then do quite a lot of work. Okay, but actually, if you use the polar coordinate for a circle, usually use a polar coordinate will be much easier. So using the polar coordinate will be like so for the polar coordinate, for every point it will be r theta rather than x comma y. So for r it will be this radius, and then the theta will be the angle from the x-axis to positive x-axis to this line. Okay, so using this one will be a bit easier, but actually we can make use of the previous case, so that to further simplify our calculation here. Of course, you can still forgetting the previous result, and then using the polar coordinate to work it out. But actually here we have already skipping part of it. Okay, because in the previous example we have the charge ring. So comparing with a charge disk, it would be something like you have many charge ring with different radius. Let's say the ring start from the radius of 0 and then gradually larger ring, and then up to here is a ring with radius small r. Okay, with a ring with radius small r, and then all the way up to the largest one, which is capital R. So you can consider this circular disk can be separated into infinite many different thin ring, 就是很 很细的，虽然它画起来就是有一个宽度，但是你有很多那种很细没有宽度的 ring，拼起来之后啊，不同半径从0到大奥的 ring 拼起来的话，就变成一个 disc， 所以它就利用这个去做积分。Okay, so here we just recall what we get in the previous example, okay, for the charge ring, okay, but here we only have contribute a small part. So here we try to rewrite this E into DE and then this Q into DQ and the other stuff remain, okay. So here we just change E into DE and then Q into DQ, okay, and then other things remain. Okay, so here it says a disk of radius R, capital R, are uniform positive charge. The ring shown has radius small r. Okay, so this yellow circle, this yellow ring has a radius of small r and radial width dr. Okay, this dr is infinitely short. And it set up a differential electric field dE at point P on its central axis. So far we do not include the assumption Z is much larger than R yet. Not include yet. Okay, we can make it later, so we just try to keep it at the beginning. Okay, so here we using the result in the previous example already saved us some time, so we already get this complicated expression. Okay, so in such a way we can try to do the integration. Okay, but before trying to do the integration, we need to do some substitution, because here we only have dq. Okay, you have no way to integrate dq. The idea is to integrate small r from 0 to r. So you should have something like integration of dr of something, and then from 0 to capital R is our ultimate goal. Okay, as much as we have an expression like this, we will be able to integrate. But if we have dq, we don't know what is the lower bound and the upper bound. Okay, so here we need to do some variable exchange. So dq will be something like sigma times dA. So last time we have a ring. Okay, so it is one dimensional. Okay, one dimensional. So we only have the linear charge density. Here we have a two-dimensional disk. Okay, so here rather than the linear charge density, we have a surface charge density 就是上一次是线的电荷密度，那这一次的是一个平面上面的，所以是一个面的电荷密度。Okay, so of course the SI units are a little bit different. It is a C over meter square. Okay, so which means how many coulomb of charge on a 1 millimeter square area. Okay, so we use the sigma to represent this surface charge density. Okay, so similarly we have the total charge will be the area, the surface charge density. The surface charge density multiplied by the area. A is the area. Okay, so here it is A only. We still don't know the relationship dA and dr. Okay, so we still need to change dA into an expression of dr. Okay, which will be something like this. Okay, you will also ask why it will be like that. Okay, so here we need to talk about a little bit about the polar coordinate more. Okay, so for the polar coordinate, suppose this is the original point, and then uh, this will be something like this. Okay, so for this part will be the small r. Okay, this part will be the small r, and then this part will be the dr, the small change of the radial distance, and then suppose this one will be theta, and in that case we can have a small angle change will be d theta. Okay, so this, I don't know how to call it, a set. Okay, so this area, so how to calculate this area is a problem. Okay, and actually this area will be the dA we want to find. It's the dA we want to find. Okay, so actually this is not a rectangle. But if we assume that dr tends to 0, d theta tends to 0, then we can approximate it as a rectangle. 我们把它当作是一个长方形，但是虽然它是一个扇形的一部分它还不是一个扇形。扇形的话应该要包含中间的部分。Okay, so if we try to assume it to be a rectangle, so this will be the height and then this will be the width. Okay, so the height will be dr. Okay, so we can quickly see that will be dr times something. Okay, so for this part, okay, so this length will be r times d theta. R times d theta will be the length of this part. Okay, will be the width of this rectangle. Okay, so this dA is actually like r times dr d theta. Okay, so generally dA in the polar coordinate will be r times dr d theta. Okay, so this is not this one yet. Okay, this is not this one yet. So why there will be a 2 pi there? So actually d theta we will consider the charge density doesn't relate to the angle. So in such a way we will have something like integration of r dr d theta, and then the dr will be integrated from 0 to 2 pi. Okay, which means that we go through the whole circle. So the d theta should be go from 0 to 2 pi. Okay, 0 will be this part, 0 will be here, or maybe here. Okay, 0 is here. So in that way the theta start to increase. So this is pi over 2 and then pi and then go back and then come back to here. So this angle will be all the way 2 pi. So that's why we try to integrate d theta from 0 to 2 pi. So in such a way we don't have theta here. So integrating d theta will be integrating a 1, so it becomes a theta, and then we evaluate from 0 to 2 pi will be 2 pi. So it turns out to be 2 pi r dr. Okay, if we go through the whole circle. So that's why we have a 2 pi r dr here. Okay, which will be the dA. Okay, so here we can substitute this actually this expression to here. Okay, so here we can see 1 over 4 pi epsilon naught is this one, and then we have sigma 2 pi r dr, and then the z we put it here, and then this denominator we also put it here. So what we only substitute is this one, putting it to here and become this expression. Okay, so here we try to do some cancellation. Okay, so we can actually cancel this pi with this pi, and then okay, it is pretty much it. So here 4 epsilon naught is here, and then sigma z is here. So the numerator at the later part is 2r dr, 2r dr putting here, and then this stuff is still there. Okay, so this is the expression of dE for this ring, and then here it's already what we expect here. Okay, we try to integrating dr from 0 to r, something like this. So we already have dr here. So what we only need is just to put integration sign here for the disk. Okay, so actually here we have dr, so it is actually 0 to r, and then we can finally get the E field generated by this disk. Okay, so this is actually like this. E equals integration of dE, and then actually we just put the integration sign from 0 to r here, and then we try to put out the stuff which is independent to r. Okay, this part is independent to dr. Okay, here we have r, here, so this part should be kept inside this integration sign, and then this part can be put in the front. Okay, so here we have sigma z over 4 epsilon naught, and then integration of 0 to capital R, 2r dr, and then over this stuff. Okay, so actually this is something to the 3 over 2 power in the denominator, so we can actually put it in the numerator, but we have a negative sign at the exponent part. Okay, so this part doesn't change, and then this part doesn't change either, but here we need to do some something like the change of variable, actually like the reverse case of the chain rule. Okay, so 2r dr, okay, 2r dr is actually this one. 2r dr is actually this one. Okay, if you are not so familiar with it, you can check out something like this: dr squared plus c squared, and then dr. Okay, so you take derivative of this function with respect to r. So r squared, take the derivative with respect to r, will be 2r, and then z squared is independent to r, so it becomes a 0. So turn out to be this derivative is 2r, and then you move this dr to the right side, so you have 2r dr, which is this one, so it will be equals to this one. Okay, we put it here. Okay, why we need to do it? Because we have a function of r like this, so we also need the d of the same function, so that we can finish this in this antiderivative. Okay, so this is just like you can consider it as an other variable. You can call it y or whatever variable you like, but here we don't actually change the variable, so we just keep it. So in your mind, if you are not familiar with it, you can just imagine this is just a y, and then this is the y to the negative 3 over 2 power, and then this is the capital Y, something like this. So it is actually a polynomial or a power function. Okay, so for the power function, the antiderivative is to nothing but add 1 to the power, and then dy this resulting power. So what negative 3 over 2 plus 1 will be negative 1/2. So we need to dy negative 1/2 in the front. So in such a way, we finish this antiderivative, and then we try to evaluate from 0 to capital R. Okay, so you put capital R into it, and then minus putting 0 into it, but here we have a negative sign. Okay, so we can put 0 into here first, and then make it a positive value. So if you put 0 into here, Okay, which means small r equal to 0, small r equal to 0, it turns out to be z squared to negative 1/2. Okay, so which will be something like this. And then if you put capital R to here, it will be 1 over square root of z squared over capital R squared. And then this 1/2 is absorbed here. Okay. So the negative sign already absorbed here. Okay, so this finite integration is something like this. And finally, we can actually distribute this z into here and here. Okay, so z cancel with this one, it turns out to be a 1, and then z is put in the numerator at for the second term. Okay, so finally the expression is something like this: E equals this stuff. Look like quite complicated. But we can still do some approximation in the next page. But so far, any questions?我简单用中文重复一次嘛，就是这一个的话，就是要算一个圆盘的一个产生的电场。那当然你可以把它切很细，切成一颗一颗，用直角坐标系就最直观的。但是直角坐标系不好算，所以他用了一个极坐标。那极坐标的话，当然如果你完全用极坐标的话，其实就多了这一部分而已。那现在的话，其实是重复利用了上一题的这个圆环所产生电场的结果。那一个圆盘的话，等于说从0到大奥不同半径的圆环拼在一起，它就变成一个圆盘了。那所以的话，就是我们利用了上一题的结果，只是把 E 换成 dE Q 换成 dQ。但是现在要积分的话，就是要有一些数学的变换。那我们最终的目标肯定是像这样的，因为我们知道那个圆环是从半径从0到2，所以我们心里面要有个数的话，就是我们一定要变成一个 dR 的积分，然后从0积分到 capital R。那所以的话就开始要换呢。那 dQ 的话，首先变成一个面的电荷密度乘以它的小面积，它就会变回来这个电荷。那这个电荷 dA 的话还不是我们的 dR， 所以还要换一下。换一下 dA 怎么换 ？dA 在这个极坐标在这个极坐标之下 ，OK， 这个就是极坐标。那极坐标的话就是直角坐标是 xy 嘛，那极坐标就是 r theta。r 的话就是它跟原点的距离就是 r，然后它跟原点的连线跟 x 轴所夹的角就是那个 theta。那这个 dA 的面积的话，就是这个部分扇形的面积。那这个部分扇形的话，因为这个 dr 跟 d theta 很小，所以我们把它近似为一个长方，可以把它当做一个长方形。长方形的话就是高跟宽，长跟宽，看你要怎么叫它。这是一个高度，一个宽度。那这个高度的话就是 dr 嘛，因为这个是其中一个 r 的这个方向，那这个是 dr。然后这个角度变化的，那这个就是弧长嘛，弧长的话就是半径乘这个角度 d theta， 所以这个宽度的话就是 r d theta。那所以这个面积的话就是 dr 乘以这个 r d theta， 就是这个东西，所以写起来的话就会像这 r d theta。那为什么会最终会变成这样呢？因为我们这个是走完整个圆周，所以这个 theta 的角度其实是从0走到 2π 走一圈的，所以我们对 d theta 的话是0到 2π 去积分但我挑了一下，就是 你可以硬写成，你可以把这个积分呢硬写成就是 r d r 就是跟 d theta 无关嘛，所以 r d r 可以写在前面，然后 d theta 0到 2 pi， 其实你可以当做它有一个乘以这个 d theta， 就是积分这个对于 d theta 的话，就是变成 theta 啊，它就会变成 r d r， 然后 theta， 然后 evaluate from 0 to 2 pi， 那就是带2 pi 减去0，就是2 pi， 就是2 pi r d r 这样。所以最终我们得到这个结果带进去，然后就是可以算一些简单的微积分，就可以得出这个结果。Okay, so here we have a simple approximation here. Okay, rather than finite field, far field assumption. Okay, we have another assumption here. We have an assumption which is R tends to infinity. Capital R tends to infinity. Capital R is the radius of the disk. If R tends to infinity, which means that this disk is infinitely large. Okay, it's infinitely large. So if R is infinitely large, so which means that R is much larger than Z. Okay, so in the pure physics assumption, we assume Z is much larger than R. Okay, so this time is the other way around. Okay, so that's why at the beginning we don't use the approximate result, we keep the original expression. So here, if we try to assume R goes to infinity, so in other words, R is much larger than Z. So in such a way, this whole thing will turn to 0. Okay, if R tends to infinity. Okay, so wow, that's great because this one turns to 0. So in this whole thing, we only have 1 minus 0, which is 1. So finally, the expression will be something like this. E equals sigma over 2 epsilon naught. Okay, so if you still remember, this is the surface charge density. Surface charge density, which should be a fixed value given the structure there. There shouldn't be any charge going inside or going outside, so it should be a constant value as at a certain situation. So surface charge density. Okay, so a fixed value. Of course, for different cases, sigma can be different, but for a certain situation, it should remain a constant value. And then for the denominator, 2 is a constant. Epsilon is also a constant. This is 8.85 times 10 to negative 12. Okay, so in other words, this whole thing is a big constant. It's a big constant. So the idea is that if this disk is infinitely large, it will generate a uniform E field. It will generate a uniform E field. That's why we need to make this assumption. If we don't make this assumption, we have this term here. Okay, so this term, it is still depending on the z. Z is the distance from the point you concern to the disk. The perpendicular distance 就是垂直距离嘛，就是这个画一点，然后上来的话就是那个 z 那如果没有这个假设的话，这一个还不是零，所以这个一的话就会跟距离有关。那现在的话，如果 r 无穷大的话，它产生的电场就是均匀的，跟它的距离无关，跟它的距离无关。Okay, so so here we have a slide calling that a point charge in an electric field. Okay, in an electric field. So here, if a particle with charge Q is placed in an external electric field E, and electrostatic force F acts on the particle. So we have F equals QE. So this is nothing but the definition of the E field. Okay, at the very beginning of this chapter. But we just move the Q to the other side, so it becomes F equals QE. Okay, so here is a highlight. It says the electrostatic force F acting on a charged particle located in an external electric field, E has the direction of E if the charge Q of the particle is positive, and has the opposite direction if Q is negative. So this is more or less the same as what we know for the definition of E field. But here we have an application for this stuff. Okay, so that's the inkjet printer， 就是那个喷墨打印机。Okay, so here let's take a look at this figure. So here we have the ink. Okay, for example, we just put the green ink here. Okay, of course you can put the other color as well. So actually, we would like to control this charge amount here. Okay, we will try to generate a uniform E field at least in this region. Generate a uniform E field in this region. Okay, so and then we try to add some charge. To a drop of ink at this point. Okay, and then we will try to shoot this ink to the right side. Okay, if there is no E field, and if you also ignore the gravitational force, that ink will go straight to the right side. But after entering this region, there will be an E field. We assume a uniform E field in this region, so there will be a force. Okay, suppose we have a negative charge. Okay, we have a negative charge added to the ink. So this charge will have a force. There will be a force acting on this charge. Okay, so this force will be pointing upward as the Q is negative. So it's just the so there will be a constant velocity movement to the right side, but there will be a force which accelerates the ink upward. Okay, 这个就是像那个抛射运动，只是上下颠倒的。对，那 okay, and then so there will be a force acting on it. So this charge will slightly turn upward. Okay, and then as much as you try to control the charge amount, as long as you try to control the charge amount at the beginning, you can actually control the displacement of this ink. 就是你透过这个电荷量去控制这个墨拐多少，然后就是投射到那个纸上面啊，它就会在不同的位置可以打印出不同颜色的墨水这样。OK， 大概是这样。OK, receiver charger. Okay, so here it says a drop shot from the generator G receive a charge in charging unit C, and then an input signal from a computer control the charge, and thus the effect of the field E on where the drop lands on the paper. Okay, 这是大概我刚才说的东西。Okay, so let's have around 10 minutes back, 12 minutes back. So we resume at 12 o'clock.